All right, today is all math,
Boo.
all the time, and so will tomorrow morning be. We're going to start with simple math and work our way up. One of the things we're going to try to get to today are some, at least one chi-square problem, since we're going to have a quiz on that either tomorrow or the next day. Start with simple math, though. Here's a graph related to an enzyme, and we're looking at, what do we call this variable down here on the x-axis? Independent variable and dependent variable. And we're looking at how much product is made by this enzyme across time. And what we want to do is find the rate of the enzyme catalyzed reaction between 10 and 20 seconds. Before we do that, where is the rate always going to be the highest at in this kind of graph? In the very beginning. Because what decreases across time? Substrate. And eventually what happens to the substrate? It's gone, right? Substrate's gone, and that's why this happens, right? What's the rate up there? 0, because the slope of that line is 0, right? To find a rate, we need to find slope. We're trying to find the slope, the rate, between 10 and 20. So the first thing we need to do is find the points at 10 and 20, right? So at time is 10 seconds. Maybe the y-axis is about maybe 7. So we'll call this 10, 7. And at 20 we're at about, what do we say there, 14-ish? 20 and 14. So we got 2 points. To calculate slope, it's what over what? Change in y over change in x. So we're going to subtract the y's. We're going to go 14 minus 7. Make sure you do the y's over the difference of the x's. We started with this y, we got to start with this x. So 20 minus 10. And we end up with 7 over 10, 0.7. And it's 0.7 in what? What are units? Yep. You take the y units, moles, divided by the x units, seconds. So 0.7 moles per second. If your line is sloping up and to the right, you're always going to get what kind of slope? Positive. If, on the other hand, your line's doing that number, you're going to get a negative answer, right? This is 0.7 moles per second. And that's the answer to the first question. Second question, find the rate between 30 and 40. Between 30 and 40, is it 0 between 30 and 40? Not quite, right? Let's erase some of this. Yeah. At 30, we're like at about 16, right? At 40, we're at probably like 17. Now, if I'd asked for the rate between 40 and 50, you would have said what? 0. Between 30 and 40, it's not quite 0. So we're going to have to go change in y, 17 minus 16, over change in x, 40 minus 30. So we end up with 1 over 10. So our rate between 30 and 40 is about 0.1. It's supposed to be a 1. And that's moles per second. And the question said, why is the rate decreasing over time? Why did the rate go from 0.7 down to 0.1 and eventually to 0? Substrate concentration constantly was going down because the enzymes were converting substrates to products. And so over time it became harder and harder for the enzyme to find the substrate, right? The rate slowed down. Does that work? Easy math. There's almost always a question on the AP exam with a graph, and it'll say find the rate of this reaction. It's almost always there. Find the slope. Change in y over change in x. Overloading my computer here, but bear with me. All right, let's do this one. Here's a crossover frequency problem. What kinds of genes cross over? What kinds of genes cross over? They have to be linked, which means they're found on the same chromosome. And if they cross over a lot, What does that mean? If they cross over a lot, they are far apart. If they don't cross over much at all, they're really close together. So let's do number 2 here. So the way I like to work these is to find the two that seem to be the furthest apart. And those would be which two? A and B, because they cross over 3/4 of the time. And I'll write those on either end. Go ahead and label if they cross over 75% of the time, or sometimes we might say 75 map units. Then I pick one that's close to either end. Which one's the closest to either one of those? C. Now C could be here somewhere, or C could be over here. And which one is it? We don't really know just yet, right? Because we don't have a comparison between what? C and B. It'd be nice if we did, but we don't. So let's pick another one. Let's pick D. D is 40 from A and 35 from B, which means where's D got to be? In between A and B, right? So D's in here somewhere. And it's 40 from here to here and 35 from here to here. That works, right? Because that gives us 75. So D's in the right place. So now we compare D to C. D to C cross over 55% of the time, which means where's C? Left or right of A? It's got to be to the left. So C's got to be there. This distance is 55. And then if you check now the A to C distance, if this is 55 and here to here is 40, it makes sense that that's 15, right? So we might write the answer to this as CADB. We might also write it as what? BDAC. Does it actually tell you the distance between A or between D and B and A and D and so on? It's an estimate, right? It's just really telling you the order of the genes in the chromosome. That's about all you get. It's called gene mapping, and it's based on how often linked genes cross over. By the way, when do they cross over? What stage of meiosis? Nope. The very first one, which is prophase 1. And genes only cross over between what kinds of chromosomes? Homologous. Same kind. Let's go ahead and do the top problem up here too while we're doing problems. So this is like a tri-hybrid problem. But we're not going to draw a Punnett square for it. We're going to use the branch method. So we want to know what's the probability that this parent and this parent will produce that baby. So I told you to think of it like 3 separate Punnett squares. And what I want you to think of first, what are the chances that this set of A's and this set of A's produce that set of A's? And what is the probability? Big A, little a, and big A, little a produce big A, big A. It'd be 1 out of 4, right? 1 out of 4. And then what are the chances that big B, little b, and big B, little b produce big B, little b? 1 out of 2, right? Draw the square for that 1 out of 2. And the chances that little c, and big C, little c produce big C, little c. Help me out. Little c, big C, little c produce big C, little c. 1 out of 2, right? So the chances that this whole thing and this whole thing produce that whole thing, they are. You got to do the product rule. You got to multiply, so you get 1 out of 16. Does that work? Everybody good with that? Any questions on that? So those should all be pretty basic kinds of math things that you all should be able to do. All right, here's the chi-square problem. Let's go ahead and set this one up. All right, so a purebred male butterfly with long wings was bred with a purebred female with short wings. Their offspring, the F1 generation, all had short wings. In the F2 generation, there are 780 flies with short wings and 220 with long wings. What's the mode of inheritance of the wing length trait? Let's say short wing length trait. So if we have a male with long wings, he's purebred, We have a female with short wings, and all the F1s have short wings. What does that tell us about short wings? It's dominant, and it's what kind of dominant? Autosomal, because sex doesn't matter here, right? So the answer to the first question is autosomal dominant. Short wings are autosomal dominant. Sex doesn't matter. If you have a gene of each, you're short. So short is dominant. Draw a Punnett square that illustrates the cross that produced the F1 flies. So let's say we're using, I guess we'll use S's. If we're using S's, this female has short wings. She's purebred, so she's big S, right? Which means the guy has to be what? If he has long wings. And it's recessive. Little s, little s. So if we're answering the second question, and we want to show how these two made those F1s, essentially we just need a one-box square. Because all her gametes are going to have what? Big S's. And all his gametes are going to have little s's, which means all their babies are going to turn out to be what? Short. They're heterozygous, but short. The second question, how do you get the F2s? Draw a Punnett square that shows this. So these are what the F1s look like. You got to cross two of those to make the F2s. So our Punnett square would look like this. So those would be short, 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 not short, long. So we're getting a 3-to-1 ratio, right? 3 shorts for every 1 long. Does this look like 3-to-1? 780 to 220. Kind of close. The purpose of our chi-square is to figure out, is that close enough that the differences are due to chance, right? So that's what we're trying to do. Before we do that, they want us to write a hypothesis concerning the F1, the F2 generation in the if-then format. So we might say something like, if short wings are autosomal recessive, then in the F2 we should get what? 3 what? 3 short for every 1 long. That'd be a good way to write it. If short wings are autosomal recessive, short wings are autosomal dominant, right? If short wings are autosomal dominant, then in the F2, we should get 3 short-winged butterflies for every 1 long-winged butterfly. Now we're supposed to do the chi-square. So when we're doing a chi-square, what's our first column? Phenotype, right? And what's the second column? Observed. Third column? Expected. Next column? O minus E. Next column? O minus E squared. And last column? O minus E squared. All over E. In this case, since this is an autosomal trait, we don't need to break this down by gender. We just need to say what and what. Short and long, right? That's it. Short and long. Even if they gave you the information broken down by gender, does it make any sense to break this down by gender? No, because it's short and long is all we're worried about. It's autosomal. So we write down our observed data. And this tells us 780 short, 220 long. So what we're going to do first is add those up and get how many? 1,000. And our Punnett square told us out of 1,000, how many should we get that are short? 3/4. 3/4 of 1,000 is 750, right? So we should get 750 here. And we should get 1/4 of 1,000 being long, and that's 250, right? So then we do what the chart tells us to do. O minus E, 780 minus 750, we get 30. 220 minus 250, we get negative 30. We square that. 30 squared, 900. And then we do O minus E squared over E. So 900 divided by 750. That's 1.2. And 900 divided by 250. That is 3.6. How do we get chi squared? Yeah, go ahead.
Is that 220 or 270 on the O on the bottom? Is that okay?
Yeah. You good? So how do we get chi squared? What's the formula? The summation of this last column, right? Summation of O minus E squared over E. So we have to add these two numbers up, and we get 4.8. So that's the chi-square value. By itself, that doesn't tell us much. We have to compare that to what? Critical value, which comes from the chart. All right, and I don't have one of those handy. Let's see if I can keep it here. All right, so do I want to keep? I want to keep those. All right, so let's see if I have a chart here. All right, before we get, while we're waiting on the chart to pull up, how many degrees of freedom? 1, because it's always phenotypes minus 1, right? And remember that when we're using this chart, which is not on this page, find the page where it is. All right, when we're using the chart, what probability level do we always use?
0.05.
Yeah, 0.05. Let's see if I don't have a chart on this one. It'll be here in a minute, I promise.
Maybe we didn't have so many tabs open.
Yeah. There it is. So we got 1 degree of freedom, 0.05 probability level. Our critical value is 3.84. So now let's go back to this PowerPoint. All right, so our chi-square value, 4.8. Our critical value, 3.84. Chi-square is bigger than the critical value. What does that tell you? We have to reject the null hypothesis, right? The null hypothesis is there's no differences between observed and expected. We're saying since chi-square is bigger than the critical value, that there's some pretty big differences. And the differences are too big to be simply due to chance. We just answered the rest of the math problem. So does that make sense? So if chi-square is bigger than the critical value, you reject the null hypothesis. Your differences are too big to be due to chance. If chi-square is less than the critical value, you accept the null hypothesis, which means your differences are small and probably due to chance.
Out of 1,000, like, is 30 either way really fast?
Big enough that it's probably more than just luck. All right, let's go ahead and work this math problem. Somebody's been playing with my PowerPoint here. Give me just a second. Adele apparently has a frequency here.
Wait, what? Oh.
And conditioner happens to be really good this year. Conditions. All right, let's see if we can't get that fixed. Somebody. Adam, was that your work? That's not your work? All right, so let's look at this one. A population of fruit flies has 396 tan individuals and 557 brown individuals. Assume that tan is the dominant allele. Calculate the following. So again, the allele frequencies of each allele. Somebody all right. Let's calculate the allele frequencies of each allele, dominant and recessive. So we have 396 tan individuals 557 brown ones. Tan is dominant. So, first thing we need to do is add up 396 and 557, right? Add them up, figure out how many people we got. How many flies we got? So we got 953. Out of that 953, 557 are recessive, right? So if we take that 557 divided by 953, we get 0.58. What does that 0.58 represent in our Hardy-Weinberg equations? If it's Q squared, right? It's the number of individuals, it's the percent of individuals that are homozygous recessive, Q squared. So we got Q squared equals 0.58. So if we take the square root of that, we get 0.76. That's Q, which means P has to be 0.24, because they have to add up to be 1, right? P plus Q has to equal 1. We just answered the first question. Q is the frequency of which allele? Recessive. P is the frequency of the dominant. The next part, calculate the expected genotype frequencies. Let's put our equation up here. Remember, it's P squared plus 2PQ plus Q squared equals 1. So the genotype frequencies are homozygous dominant, heterozygous, homozygous recessive. We already got the homozygous recessives, 0.58. So to get the heterozygous ones, 2 times P times Q. So let's go 2 times 0.24 times 0.76. And when we do that, we get 0.36. And then for homozygous dominant, it's P squared. Let's go 0.24 squared and get 0.06. So the way we would write that answer is we would say 0.06 homozygous dominant, 0.36 heterozygous, and 0.58 homozygous recessive. So that's B. So we got A, we got B. The number of heterozygous individuals that you would predict to be in this population. So we had 953 total flies, right? And we're saying that the heterozygous one should be 36% of that. So if we go 953 times 0.36, so we got about 343 heterozygous individuals. Again, that's the total population size, 953 times the heterozygous 36%. The expected phenotype frequencies. How many phenotypes are there? 2, tan and brown, right? And both of these are going to be what? Yeah, they're going to be tan, right? Because tan's dominant. This is brown. It's recessive. So what are our frequencies? 0.42 tan and 0.58 brown. That's it. 0.42 tan, 0.58 brown. Phenotype frequencies. And then E says, conditions happen to be really good this year for fruit fly breeding. I should say breeding. Somebody's been having fun. And next year, there are 1,245 baby flies. Assuming that all of the Hardy-Weinberg conditions are met, how many of these would you expect to be tan, and how many would you expect to be brown?
I think you just can't spell.
No, I can spell. That's somebody having fun.
I don't know.
Here's the deal, though. Hardy-Weinberg conditions are met. What does that mean about P and Q? They didn't change. What does it mean about all these numbers up top here? They didn't change because evolution didn't happen. So if we had 1,245 babies, we just got through saying that 42% of them should be what? 10. So let's go 1,245 times 0.42. So 522.9. Those should be 10. And 58% should be brown. So 1245 times 0.58, we get 722.1 grams. And that's that. Does that work?
I have a question.
Yes.
So, since we're talking about animals, would you round those numbers to the nearest?
I would go ahead and leave it as a decimal. I mean, it might be 522, it might be 523.
I mean, how do you have 0.9?
Right, you can't. But go ahead and leave it as a decimal just so they know you did the math right. Realizing you can't have 522.9 plus. That would be weird. But go ahead and leave it that way. All right, let's go ahead and work this one here too. After graduation, you and 19 of your closest friends, let's say 10 males and 10 females, charter a plane to go on a round the world tour. Unfortunately, you all crash land safely on a deserted island. No one finds you, and you start a new population, totally isolated from the rest of the world. 2 of your friends carry, or heterozygous for, the recessive cystic fibrosis allele. Assuming that the frequency of this allele does not change as the population grows, what will be the incidence of cystic fibrosis on your island? So here's the thing. Starting out, does anybody have cystic fibrosis? No. But there's 2 people who are carriers. If this is a small, isolated population, is cystic fibrosis eventually going to show up generations later? Yeah. So what we got to do first is find P and Q. We have 20 people, right? You and your 19 closest friends. 20 people. So how many alleles do we have? 40, right? 2 apiece. We got 40 total alleles. And out of that 40, how many of them are cystic fibrosis recessive alleles? 2. So 2 out of 40, that represents what? What variable? Q, right? The frequency of the recessive allele. That's Q. And 38 out of 40, that's P. That's not cystic fibrosis. That's normal, right? So let's convert those to decimals. 2 divided by 40. That's 0.05. That's 0.05. This has to be what? 0.95, right? So this says Hardy-Weinberg conditions are met. Allele frequencies don't change from generation to generation. But if we want to know 5 generations from now, how many people are going to have cystic fibrosis? Not how many people, but what's the incidence? So what's the frequency? How are we going to calculate that? In our equations, what are people who have cystic fibrosis going to look like? What part of our equation? People that have this. Q squared, right? So let's take 0.05 squared. So that tells us that 0.0025. That's the frequency of people with cystic fibrosis. So 0.25%. Because if that's frequency, if we wanted in percent, we have to move the decimal 2 places, right? So cystic fibrosis is not going to be too common. The only way it's going to be common is that if we get some what going on here. What could make it common? What happens in small, isolated populations? Genetic drift. If one of these 2 carriers happen to be really fertile people, and they made much as babies, what happens to that Q number? It goes way up. And then what happens to the Q squared number? It goes, Q goes up, Q squared goes up too, right? So it could happen, but they're saying in the stem of the question here, that doesn't happen. They're saying the P and Q stay the same. All right, let's work 1 or 2 more things before we call it a day. I don't want to do those yet. All right, let's do a couple water potential problems. Let's start with this one. First of all, remember that water potential, what's the symbol for it? Yeah, psi, it looks like a trident, right? So we'll say psi total has 2 parts. What are the 2 parts? Pressure plus solute potential. We're trying to find the total water potential. We're trying to find psi sub t. We have a solution that is made of glucose. It's in an open container. The concentration of the glucose is 0.3 molarity. The pressure of the solution is 0. What is the total water potential at a temperature of 37 degrees C? All right, it tells us the pressure is 0. That's 0. So we got to find the solute potential. What is the equation for solute potential? Negative I C R T. All right, one thing you got to know, this is glucose. What kind of compound is glucose? Yeah, but it's molecular. It's covalently bound together, right? What's I for covalently bound together things? 1. It doesn't turn into ions. It just stays sugar. So if it's any sugar, this I is going to be 1. What's C? It's the similarity, 0.3. And I'm going to write that big M stands for moles per what? Liter. What's R? It's the gas constant, which is given to you on your formula sheet, but it's 0.0831, and it's C. That's a 1. Let me erase that. 0.0831, and it's liters times bars over moles times what temperature unit do we have to use?
Kelvin.
We have to use Kelvin, so that's K. So that's R. Then we have to multiply all that by T, and again, T has to be in Kelvin. So how do we change Celsius to Kelvin? Add 273, so 273 plus 37 is 310. Cancel out units we can cancel out. K's, moles, liters. We're left with bars. So we do the math here. We got 0.3 times 0.0831 times 310. And we get solute potential of negative 7.73 bars. So we take that, we plug it in right here. Since the pressure was 0, it doesn't really matter. The total water potential is negative 7.73 bars. Now, let's say we took that solution. So here's our solution, and in here is water potential of negative 7.73. And we put a cell in there, put the cell in that solution, and the water potential in the cell is negative 10.5 bars. What happens to the cell? Does the water go in or does the water come out?
Go in.
How? All right, in the beaker is negative 7.73. In the cell, the water potential is negative 10.5. How does water potential move water? From higher to lower. Which is a bigger number, negative 7 or negative 10? Negative 7, okay? Which means water is going to move from the beaker into the cell, from higher to lower. Negative 7 is bigger than negative 10. Let's do one other thing before we go. Let's say that we leave everything the same in this problem, except we change the glucose to potassium chloride. So instead of the solute being glucose, it's KCl. Well, that changes things, because what's KCl? What kind of compound?
Salt.
It's a salt. It's a metal and a non-metal. And when you put salts in water, what happens? They break up into ions, right? They ionize, they dissociate. In KCl, when you put it in water, what does it break up into? With 2 ions. K what? Plus and Cl minus. What's the ionization constant for that? 2. You count how many charged particles you get. You got 2 charged particles. 1 positive and 1 negative. So I for that is 2. So if we were calculating the solute potential, it would be negative 2 times 0.30 concentration times R times 310. So that's just going to change our answer by a factor of 2. So 2 times 0.3 times 0.0831 times 310. And this time we end up with negative 15.5. So if it's sugar, I is 1. If it's a salt, you have to break it up into ions and count how many charged particles there are, and that's going to give you I. How many charges. If it was calcium chloride, for example, what does that break up into when you put it in water? Ca what? Ca plus 2. My marker just decided to stop working, but Ca plus 2 and what? 2 Cl minuses. That's what ionization constant. That's 4. You got 2 positives and 2 negatives. 4. I would be 4. And that's where we will stop.
Sleep.